Alright, guys, you're welcome to the deep learning paper series where we pick some important papers in literatures and we try to dissect it to understand what are the ideas behind the papers. So today we'll be looking at on the power of curriculum learning in training deep networks. Essentially, the key important thing here is the curriculum learning, and the idea is taken from the educational institution in colleges, universities, and high schools. You always have what you call a curriculum. Now, what's a curriculum? It's a plan of how you are going to teach the course or going to teach the subject or whatever it is you want to teach. So you essentially plan the course in such a way that the fundamentals, the terminologies, the easier concepts are presented first to the student, and you now build on this gradually until you get to a point where you start explaining the more complicated, the more complex, the more difficult concept in the course. So the the people that worked on this research picked that intuition and said, can we use that same knowledge to be able that same concept to train neural networks? How does the way we present examples to the neural network, how does it affect the performance of our network, of our model? And it happened that the way what they call the pace here, the pace or the order, that is from the less difficult to the from the easy ones to the more difficult examples, those significantly affect the performance of the trained network. So that's essentially what this is trying to say. That's the whole summary of the work there. So we just look at some of the important points. Now, for them to be able to employ curriculum learning, they have to resolve two problems. First is they have to answer the question of how are we going to sort the training examples by difficulty. Now, for instance, in classrooms, like I made mention earlier, you the teacher, you the instructor, you know which are easier examples and which are difficult concepts. You know the easier concept and the difficult concept. So you can easily arrange your course in such fashion from the easy ones to the more difficult ones. But how are you going to tell the neural network or find out from the neural network or how are you going to look at training examples and classify them as difficult or easy? It's kind of weird. So you give me an image of a dog, an image of a cat, or image of a house, image of a car. So which one is more difficult than the other? It's very difficult for me to actually arrange those sets. So that's the problem of how to sort the training by difficulty. Another problem is how do we now complete a series of mini batches that exhibit an increasing level of difficulty? That's another challenge, because if you're conversant with neural network, when you feed in your training examples into your network, you don't do them all. If you have 1,000 training example, you don't put all the 1,000. You want to break the 1,000 into maybe batches of 32. 32, 32, 32, something like that. So how do you now arrange your training examples and say this batch of 32, it's the first batch of 32 is the easy one, the next batch of 32 is the uh, next difficult one, the next batch of 32 is the next difficult one. It's you might want to say, okay, if you are able to solve problem one of sorting your training examples by difficulties, let's say from 1 to 1000, then you just say 1 to 32, those are the first batch. Then you say 33 to maybe to 64, that's the next batch. But then come to think of it, when you're training a network for different classes of training samples, you're going to have what you call, let's say you have a binary classification task, so you're going to have some samples, maybe you're classifying a tumor and no tumor. So you're going to have in your first 32, are you going to make all your the first 32 to be all tumor samples because diagnosing a tumor maybe is easier, or non-tumor, those that don't have tumor, maybe that is easier, and you make the first 32 non-tumors, then the next 32 non-tumors. Then by doing so, you are introducing imbalance in your training. So that's the challenge there. So the way they address this problem is, first they did transfer learning from some competitive teacher network. So, and we're going to look at that, and bootstrapping. So what they were doing in the transfer learning, as we will see later on, is they have a network that have been trained on other tasks, and they now use that network to do a classification. They run each of the training example on that network, and they see the confidence level of that network. For instance, when you run the network on an image of a cat, maybe you can say I'm 75% confident it's a cat, or they run it on the image of a person and it says I'm 99% confident that it is a person. So that means to that network, the image of a person is easier compared to the image of a cat. You get the intuition. Another way they solve the problem is by bootstrapping. Bootstrapping is training a fresh network that have never been trained before. You train that network on your data set that you're experimenting with. Then it's just like a self-training. So after training the network on that data set, then you now use the network to actually make a classification score to give you a score, prediction score on the training set. So in the evaluation, both methods show similar benefit in terms of increased learning speed and improved final performance on the test data. And so that's essentially, and they use some data set there. So let's go to the some important point here. So the scoring function is used to determine the difficulty or complexity of each example, like I mentioned. So you need to have a scoring function that is going to output a regression value. It's going to output a number. Then you will use that number to sort your training examples. That means you have to run each training example through that scoring function to be able to find out the difficulty. So the scoring is done based on transfer learning or bootstrapping, like I said. Now the second function is the pacing function. It talks about how many samples do you present to the data at once. do you present to the network? Sorry, how many training data do you present to the network at once? You know that even if you arrange your in a classroom, you arrange your concept, the topics from the easiest to the most difficult, and you decided to teach all of them in one day. You have not made any difference because the students have not assimilated the easier ones and master it before you have built on the difficult one. That's what the pace is saying. So okay, you want to train your network and let it be good on the easier one before you now build on top and present it more difficult one. So, and that depends on the data itself and the learner. So we'll see the function shortly here. So let's see the algorithm here. So this is the whole thing. So this is the curriculum learning method. So your input is you are putting in your pacing function and your scoring function. Just a function is just a mapping from input to output. So here, and you put in your data X. So and you have to output a sequence of mini batches that is sort in ascending order. That will sort your training data from the lowest, from the easy to the difficult one. According to, so it's going to sort it according to your F, which is your scoring function. So yeah, you initialize an empty list, you iterate through your number of batches that you want. Let's say you want 50 batches or 10 batches, whatever you want. So for you to get the first batch in your training set, you give a size to that. So the size is determined by GB. This is your pacing function, which says how much should you have, how many samples should you have in the first batch. Then you take that number of size from your training data from X. You take that from your X, and then you uniformly sample the first batch from this your X prime. Then you append that to your result and you return your result. So essentially that's what's happening here. Here you have your training data from maximum of n training samples, and each of the samples is denoted by xi, yi, and these are the labels. That is yi, which can be of the number of label, which if it is binary can be maybe 0 or 1. So your pacing function, you are trying to map your M, which is the number of batches that you want, to the total number of training samples that's available. So you define your pacing function, which can also depend on your classifier. So you use your pacing function to determine the sequence of your training samples that you are going to feed in. So they were also experimented on anti-curriculum algorithm, which is just the inverse of curriculum. Here you arrange from difficult to easier ones. You also have the traditional one, which is a random, where the training samples are randomly scored. So now for you to be able, in their work, they experimented with different types of pacing function. You have the fixed exponential pacing function. What this is saying is that you as the number of iterations in your training proceeds, you give it certain fixed number of training examples. Let's say here they give it roughly like, okay, 500. So after a certain number of iteration again, they give it another number of values. So what they are saying is that they give it a fixed, within fixed number of iteration, within fixed number of every 500 iterations, they increase the number of training samples that is presented to the network exponential. In this case, in varied exponential pacing, it says that they present the number of they increase the number of training samples that is presented to the network exponentially, but not at fixed number of iteration. They did that at arbitrary number of iteration. That is what is represented in the dash green. And you have the last one, which is single step. So they use a particular number of training samples up to like half of the training, and they presented the remaining one at the other half of the training. They just exponentially increase the training samples and get it fixed it to the end of the training. So these are all represented here in these formulas. So you have all this represented here in the formulas. Okay, so let's see some other important thing there. So we've mentioned curriculum by transfer, which you use a trained network, and these are some of the results. So let's take this for instance. So this is top 1 accuracy. Top 1 is saying essentially that if the class, the ground truth is a cat, how many and your network present a cat, then that matches, that means it exactly match the ground truth. That's the top 1. Top 1 is just saying the exact prediction. It's different from like top 5, where you are saying, does the ground truth is the ground truth present in the top 5 probabilities that your network is predicted. Alright, so here you see the batch number. The blue is the curriculum learning. You can see that as you increase the batch number, you see that the accuracy of the curriculum learning kept on increasing, and the vanilla, okay, you see the random, which is in the green, is when you actually does it randomly. So you can see here, and the blue, the red is the anti-curriculum. You can see clearly that the curriculum did pretty well. The same thing here, you will see that the curriculum did very well. That's the one in blue, had a higher performance. And so the same was also observed here. You see that the curriculum in blue did very well. Okay, so that's essentially what the work is all about. That's essentially what we have in this paper. I don't think I'm missing any other thing there. Alright, thank you guys, and if you have any contribution or comment, do leave it below in the comment below, and let us know how well you understand the concept presented in this work. Thank you very much. See you in the next one.